Hi, everybody. Wow, this is just really cool, seeing a room like this full of people who want to learn about Postgres. Seeing Postgres grow over the years and decades, and now we have a room full of people here learning about Postgres. So, I'm Jim Oljenski. I am a database engineer, a principal database engineer at AWS. I'm part of the Aurora Postgres and RDS Postgres team. And unfortunately, we have a crippled screen over here, and we have a clicker that doesn't work, but we'll go on. So we're about halfway through reInvent now. We're the middle of the day of the middle of the week, and a lot of the Postgres sessions have already happened, but there's still some more related sessions that are coming up throughout the week. There's also a new one that just recently launched about learning about RDS on VMware. Check that out for a deep dive into that. That's tomorrow. But what is Relational Database Services, or RDS? It's a simple way to run your relational database in the cloud. It's available in 6 different engines, cloud native of Aurora, and it comes in the flavors of MySQL and Postgres. You also have the open source engines of MySQL, MariaDB, and Postgres, which we're going to focus on today, and the commercial engines of SQL Server and Oracle. When you want to run Postgres on AWS, you have a few different options. You can run it self-managed on EC2 and put your data on EBS volumes. Or you could run it in a managed service, either through RDS for Postgres or Aurora with Postgres compatibility. And now the clicker's working. Cool. But when you're doing that, you have a few different choices. You might have Postgres being open source. Some people have really customized Postgres, building it with custom configuration options and doing that. When you have something like that, you're going to have to run it in a self-managed environment. And when you do that, your DBAs are going to have to take on more work of setting up the platform, installing Postgres, configuring high availability, and monitoring and whatnot, and they don't have as much time to deal with application level problems. When you use it through a managed service, your DBAs now have time to work on the business critical problems, whether it's doing schema design earlier on in the process, so this way you have good schemas as you're building your applications, or doing query tuning. RDS and Aurora Postgres will take care of the platform issues for you. So RDS for Postgres closely follows along the Postgres community's release cycle. The Postgres community has yearly major releases. They're released out in the early fall. And you notice the major release numbering scheme has changed a little bit. It used to be at the DAT release, so 9.6 is a major release over 9.5. But starting in Postgres 10, it started having the first number as the major release. So 10, and then the latest major release is Postgres 11, which is available in the preview environment if you want to test with some of the new features and functionality in Postgres 11, and we'll talk about some of that today. Also, Postgres has quarterly patch and update maintenance releases. Apply them quickly. They're usually there for bug and security fixes. So Aurora is built from the ground up, leveraging AWS services. It gives you some additional performance characteristics, and it'll automatically scale your storage up to 64 terabytes. You don't have to pre-allocate the storage, it'll scale it with you. And it gives you additional durability and high availability options. And speaking of high availability, how do you set it up, Postgres, with high availability? The first thing you do is backups. Even if you have automatic failover or replication or anything else, any database, you need backups. Any database you care about, you should be taking backups. That includes your development and your testing instances. You may want to be able to roll it back from a change. Having those backups will help. With RDS, you have the ability to just click and set up daily backups. Your backups will run during your backup window, and it'll take every 5 minutes, take a snapshot of your transaction logs and be able to save that off. So this way you don't lose any data in the event that you need to restore from backups. When you're setting it up for production, by default, RDS will give you a 7-day retention. Set that up for more like 3 weeks. You could have it up to 35 days retention. It's not uncommon that you want to be able to go back and look at a backup from a couple weeks ago to help diagnose a problem you're experiencing today. So if you have those backups, you can go back and look in time. But when you're talking about backups, the most common reason you're going to restore from backup is not because of some catastrophic failure on your database server. It's because of human error. Somebody accidentally dropped a table, truncated a table. There was a bug in a data maintenance script that you need to go back and fix some of the data. With point-in-time restore, you can restore your database to the instant before that event happened. And you don't have to restore it back to that main database. You could restore it to another instance. And it doesn't have to be the same instance size. A lot of times, if you want to get back that dropped table, you want to temporarily restore it. There's no reason to restore it to the same instance type that you had in production. It could be smaller with a smaller amount of IOPS in order to get that table back and load it back into production. But for any production server, you want to set up automatic failover. And with that, you'd set up multi-AZ. With multi-AZ, you're synchronously going to replicate your data out to a second availability zone, and in an event of any sort of failure, RDS will automatically promote that standby and redirect your DNS entries. So this way, your application will reconnect to that, and you'll be serving your customers again. But with a highly available database, you need to secure it. And for anything with security, you start with communication to the database. You want to have encrypted communication to the database, same way you do to your web servers. You want to use SSL. Even if you're running everything in a protected VPC, a lot of times DBAs may connect from their laptops and other things. You want to ensure that everything's encrypted across the entire path to your database server. When you create a new RDS instance, there's an SSL certificate on there that you're able to leverage. And it's optional. It's there optional, but what I recommend is turn it on all the time and you set the parameter force SSL. You even want to do this on your development servers, because a lot of times you'll take data from production, roll that back into your development servers, and this way it's encrypted all along. But with encryption over the network with SSL, it is a two-way communication between the client and the server. So the client also has influence over that. It will request the type of connection that it's going to have. So with Postgres, how the client requests the type of SSL connection, it's by setting the SSL mode parameter in your connection string. There's 6 different options there. 2 of them, disable and allow, never use. When it's set like that, you're probably going to be sending things over clear text. The default is prefer. When it's set with prefer, if SSL is enabled on the server, the client's going to use an SSL connection. So by default with RDS, having SSL enabled on the server, and set the default client having it for prefer, by default you're going to have SSL connections. But really what you want to do is set it to require. Just in case somebody disables SSL on the server, you want to have that client also saying, I'm only going to talk to you if your network is encrypted. So this will guard against disabling that SSL on that server. But you might have higher requirements from a security perspective, where you could set it to say verify CA. What that'll do is verify that that certificate coming back from the server is from a known certificate authority. This will essentially verify that you're connecting to an RDS server. Prevent somebody putting another Postgres instance in between or something else that's responding on the default port. It'll ensure that it's coming back the right way. But you may have even more stringent requirements, and you want to verify the host name as well. And setting it to verify full will verify the host name. Be careful with that if you have things where you want to spin up multiple read replicas and you want to load balance across them, or you're setting a DNS entry for convenience. It'll verify that the host name over the host name given to you by RDS when you create that database. So if you create different DNS entries on top of that, these connections will fail. But when you have a secure communication, now you want to authenticate and connect to the database. Postgres, by default, uses MD5 with Assault for authentication to authenticate against database users. You'll create your user and give it some sort of strong password. You could have a valid until if you'd like. And that works really well for a lot of people. In a lot of cases, that's enough security for them. But some people have more stringent requirements. Some people have 5,000 or 10,000 Postgres databases, and they need to centrally manage their users. In the event that a user leaves the company, you want to be able to disable access for everybody, for that user for all the databases. You also may have more complex password requirements. In order to accomplish this, you have the ability to authenticate with identity and access management. You could just enable it for your RDS and Aurora Postgres databases. There we go. And when you do this, you're authenticating against IAM, and from IAM, you're getting a token that lives for 15 minutes, and using that token in order to be able to connect to Postgres. So this way, you're never authenticating directly against Postgres. It's leveraging IAM for that authentication. And Postgres will go out and verify that against IAM that you have a valid token. How do you configure that? So you now have a new role inside of your Postgres databases as you update to the latest versions, RDS IAM. So if you have existing users that you now want to enable IAM authentication, you just grant that role to that existing user. You also have the ability to create new users and also grant that role. And notice on that create user command, we're not setting a password because Postgres isn't using that password. You're authenticating against IAM, not against Postgres. Postgres is trusting IAM to say that that user is valid. So you have to create a user account within IAM. When you're doing that, set it as the same name as the database user. It just simplifies management and administration of that. If you have different names, trying to associate them could get tedious. Having the same name makes it simpler. Also, that user needs programmatic access in order to be able to generate a token. Once you have that user, you need to grant it a policy for RDS DB Connect. In that policy, you have to give it a little bit of information. What region is this database in? What's the account that that database is in? Most importantly, what's the database ID? Here you could give it a specific database ID, but give it the wildcard star, because if you spin up a read replica off of that master, or if you try to restore a database, you'd have to change your policy in order to log into that restored database or that read replica. By giving it the wildcard, you restrict it down to the databases within a region for a given account. And then finally, you have to give it the database user you're connecting to. This is the association between the IAM user and the database user. Again, keeping everything all the same just simplifies things. And then when you connect, you need to generate that token. Whether or not you're connecting with Postgres via the command line that we're going to see here, or you're using one of the GUI tools like pgadmin, that token is essentially used as a password. With Postgres on the command line, you have the number of different environment variables, like PG password. So if you set the result of the generate DB auth token command as the PG password, you can now use that. And this is what that token looks like. If you were connecting with the GUI tools, you would copy and paste that token in order to connect. But on the command line, you don't have that because you're set it via the environment variable, but it does require SSL. So once you're connected, you need to authorize different objects within there. You have the same ability that you do in other databases of locking down individual objects. Postgres allows you to grant and invoke privileges on individual objects to different users and roles. So you could revoke update privileges to your BI user. You could also go more fine-grained at the column level. So you could revoke select privileges from everybody for a sensitive column like social security number. Postgres also has row-level security. So you could create policies on something like a sales table. So a sales manager could only see the rows that he or she is allowed to see, given through your policy. So once you have your database, invariably it's going to scale. Your databases are going to get bigger. You're collecting more and more data. So you have a number of different instance sizes for RDS that you could use, everything from a small T2, one virtual CPU, up to a 96 virtual CPU M5 instance. You could also scale your storage. You can now scale your storage in RDS up to 32 terabytes and have 40,000 provisioned IOPS. But with any given instance, you want to take the best advantage of the resources that are in there. And a not uncommon scenario in a lot of schemas, you have one or two really large tables and a lot of other small ones. And within that, it's also not uncommon that you have a small set of hot data and a lot of historical data. Maybe it's a sales table that you're always dealing with the most recent sales orders, and last year's and 2 years ago sales orders you only do on yearly reports. Those sorts of scenarios is prime example of for something that's a good candidate for partitioning. What partitioning is taking one big large table, splitting that up into multiple small chunks, and making that appear as one large table out to the application server. This gives you a couple advantages. One, in performance. When you're running your queries, Postgres is able to prune away large amounts of that table even without accessing it. And also around maintenance. If you need to perform maintenance operations on the partitions, it's on lot smaller chunks. And that's not something new that's been in Postgres. Postgres has had table partitioning for 15 years. But how it's been done is, it used to be done via an innovative technology called table inheritance. Postgres has had table inheritance that allows you to create child tables underneath those parent tables, and you restrict access to the individual partitions or child tables based on constraints. And then Postgres would use those constraints to prune away the partitions. But because you would use table inheritance for other things other than just table partitioning, Postgres didn't have the ability to know how to route the data into there. So before Postgres 10, you had to create triggers in order to route that in there. Right? I like writing code and all, but writing partitioning triggers is not always a fun thing to do. It's just the overhead of doing that, and you're adding overhead of just writing a trigger in the first place. Starting in Postgres 10, we now have partitioning syntax. And what this allows us to do is create actual partitions on there. We're giving Postgres more metadata about what we're trying to do with that table, as opposed to just straight table inheritance. We could have a lot of other uses. Here, Postgres now knows we want to use it for table partitioning. But like any large feature in Postgres, it really is something that evolves over time. With yearly release cycles, Postgres iterates on large features like this over and over again. So in Postgres 10, if you wanted to create an index on the parent table, you would get an error. You'd have to create it on all the individual tables, partitions themselves. But in Postgres 10, we did get that partitioning syntax for range and list partitioning. And the big thing is that triggers are no longer needed, giving us a big performance gain on our data loads. And what those performance impact are, so if we had that orders table that we've been looking at, we wanted to load in 7.5 million rows, which is about a gig of data. With the old version, with table inheritance with triggers, that would take about 8 minutes to load. With the new partitioning syntax, now that same amount of data loads in about 40 seconds. But more than a 10x performance gain, giving us performance very close to loading data as if there were no partitioning at all on that table. But Postgres does continue to evolve in Postgres 11, again, which is available in the preview environment. You can now do things like creating indexes on the parent table, and that will push down the indexes onto the individual partitions. You could also now create primary keys and foreign keys, which you couldn't do before. Also, it has the ability to move data via updates. So if you update a column, that's the partitioning key, which would force that row to move to a different partition. Postgres will now move that to the different partition. You also have default partitioning. So this way, if you have data coming in with, say, a date you weren't expecting, say January 1st, 1970, and there's no partition for that, that row would be pushed into that default partition. The biggest advance is really partition elimination at execution time. Before Postgres 11, Postgres would only prune away those partitions at optimizer time. So you'd have to have something in your where clause to tell Postgres, eliminate all those other partitions. But that's not how people write code. People write code by joining to other tables, and you want to be able to prune via that join. So here's an example of just summing up all the sales orders for the Mondays in Q2 of 1992. Right? We know, if we wanted to get that with monthly partition, we really only need to access 3 partitions. But Postgres can't interpret that by just looking at the SQL. It's really getting that back from that dates table. So with Postgres 11, now it can do it at partition pruning at execution time. That's a 35% performance improvement by being able to prune that at execution time. And that gives us a huge benefit over what Postgres 9.6 was, which was a 74% improvement over the old way of doing table inheritance. With that, I'm going to turn it over to Jeremy.
Thank you, Jim. It is fun. All kinds of stuff to talk about with Postgres.
Push hard.
And I hope you still have lots of room in your brain. I'm going to use the rest of the time that I have today to talk about 2 more topics that I think are important to cover this year at reInvent related to Postgres. And the first one is maintaining multiple copies of our data. We're all doing this, right? In fact, I've put an example of one of the reasons on the screen to your left. Right? High availability, that's one reason. Another reason might be you want to squeeze that downtime window as small as possible while you're doing a major upgrade, or maybe you're moving from one platform to another, right? Maintain those multiple copies. You might need access to more compute capacity than you can get from the biggest single server available. Another thing might be that you have a geographically distributed application. You want to move your data and your apps as close to your end users as possible all over the world. These are all some of the different reasons that we want to do replication, maintain multiple copies of our data. And Postgres, as we've been talking about, this isn't a new database. We've been around for a couple of decades. The database has. And replication is nothing new. The first production replication solutions for Postgres were over a decade ago. Now, in RDS Postgres, we have 8 patterns for replication that are really common. And I want to run through all 8 of these real quickly. And the first category is what I'll call sort of SQL-based. But really, there's ways you can do replication where you don't need anything special from the database outside of the SQL standard. First of all, you can manage it entirely yourself outside of the database. Or secondly, there are replication solutions that are based on triggers. This is the oldest way of doing replication in Postgres. This is what's been around the longest. And you might be tempted to think because it's been around for so long, maybe it's getting obsolete. But that's not the case. In fact, I've talked to people just this past year where, in spite of the complexity and the cost, and it made sense for them to manage it themselves. Or another thing to think about, you could have a Postgres database in one of your data centers that you haven't touched for like 10 years. You could still use a trigger-based solution on that database to move that data pretty much anywhere you wanted to. However, there are still some drawbacks to these approaches. If you want to manage it yourself, there's a lot of complexity there. There's a lot of corner cases, and it's your responsibility to cover all of this. You also have to own the maintenance of that. So that's hard. That's expensive. Trigger-based solutions, these have been around for a long time, and they're very well understood. It's also pretty widely acknowledged that they increase the write I/O load on your source database, and there's also a noticeable CPU overhead that you get. So the thing with these drawbacks, if the clicker will go for me, is that you can't really solve these problems by just tuning some parameters, right? They're inherent to the approach. If you want to solve this problem of having all of this inefficiency and you don't want to have all the complexity of managing it yourself, we need to take a different approach to replication. And that brings us to a whole different approach, which Postgres, again, brought in still around a decade ago now, which is physical replication. Now, if you're not familiar with the concept, in a nutshell, what physical replication means is that at the end of the day, your replica, your copy, kind of looks almost like what you would get if you just copied the files from one server to another. And this is not the way SQL-based replication works. You can have the same schema. You can have the same rows, the same data. You could even run the same SQL statements in the same order on 2 databases. But if you open up your files in a hex editor, what you're going to find is they don't look the same. For example, the transaction identifiers and the data structures that are underneath your tables, those are going to be different. In fact, I have to sort of take a short tangent here and point something out that you can see this for yourself. And if you're on Postgres 10.5 inside of RDS, in fact, this screenshot here, this is an actual screenshot from a hex editor that you could use. to open up your Postgres data files from RDS and take a look at the byte level, what's going on there. The color coding in this hex editor is taking each individual byte, and it's mapping that byte back to the data structure in the source code of Postgres that you can download from the internet. It's a level of transparency that's absolutely amazing. I'm really excited that we're able to give that capability. In addition, you can also use SQL. There's an example at the top to query against the data structures that are underneath your tables. Right, and coming back to Postgres and replication, so physical replication. Yes, let me just move on to the next slide. We have basically two patterns for physical replication in RDS. Multi-AZ we introduced earlier. So multi-AZ is the checkbox that you hit. And the great thing about multi-AZ is that you don't have to worry about tracking the state of your cluster. You don't have to manage the endpoints. And you don't have to try to make sure that you configure your database so that it's impossible to lose any data. We've done all of that heavy lifting for you and made sure that it's set up properly. So the only thing that you have to do is check the box. That's the reason that we do recommend to pretty much all of our customers for your production systems to use multi-AZ. In the second pattern for doing physical replication in RDS, and I want to be careful here. So on MySQL RDS, the read replicas are not physical replicas. Those are more like, they're logical replicas. They're more like what I was describing earlier. But we're here for Postgres, and in RDS Postgres, read replicas are in fact physical replicas. So we benefit from the efficiencies of just moving the log records across. So whereas multi-AZ is designed to give you higher availability, read replicas have a different goal. Read replicas are designed to allow you to run queries against your replica. Even if that replica is on the other side of the planet in a completely different region, you can run your queries there. There are still some drawbacks with physical replication, though. Maybe you guessed I was going to go there. First of all, you can't just replicate when you're doing this kind of a model. You can't pick one table out or just part of your database and replicate that. Another thing is that you can't go across different major versions of Postgres. Another thing is that you can't, in your replica, your copy, you can't make another table that you start doing writes on that table. It's pretty much read-only. So we've solved the inefficiency problem that we had with SQL-based replication. We don't have all that additional I/O and CPU overhead, but we've lost all the flexibility that we had. And this brings us now to Postgres's answer to that, which is to build a replication solution that can meet all of these needs. Now, I'm going to start from the bottom, and I want to kind of step through how this thing is built, because I think there's some really important lessons to learn as we look at this. Remember that one of the first problems we were trying to solve was a write amplification problem, really. That with triggers, when I flip that switch to turn on replication, now every time I make a change to the database, instead of one write, I have to do two writes, because I have to make my change, and then I have to keep track of that change over in some other place for the replication stuff. There's a simple solution to that, and it's used in a lot of databases. Every modern database has a log, and that log, it could be called a redo log. We call it a write-ahead log, or we say wall for short. And that log, every change in the database just goes into this log. Well, the simple solution for that double write problem is that we take advantage of the log. We already have all the changes in this log. If we can just start reading that log back and using that, then we don't need the second set of writes for replication. And that's exactly what Postgres did. The very first, earliest physical replication solutions for Postgres 10 years ago were we just copy those logs over to another server. We replay those logs on the second server, and bingo, we've got a physical replica. But there's a problem here. The problem is that I have to wait for the file to get filled up before I can copy it across. So my copy might be 5 minutes behind. It could be up to like 30, depends how you configure it. So to solve that problem, Postgres introduced something called streaming replication. And the key thing here is this new process called a wall sender. It's a process that runs on your database server. And what this process does is that instead of waiting to fill up the file before you copy that file to your second server, this process can, as soon as possible, send those bytes over the network to your replica. And this works beautifully. With streaming replication, in Postgres, even on old versions of Postgres, your replica, your physical replica, instead of being a matter of minutes behind, it's now seconds, if not milliseconds, behind the master. But there's still another problem. Because what if I have to, for some reason, shut down my replica for a while? I have to do some maintenance, or there's a problem. And while it's shut down, the source system is happily chugging along, and he goes through, and he didn't need all those logs, so he cleans some of them up. And then I bring my replica back online. Well, that wall sender process can't send the changes because they're gone. So now I have to go to my backups, pull the logs out of my backup system, apply them the old-fashioned way. This is not optimal. To solve that problem, Postgres introduced something called replication slots. And really, it's just a little bit of metadata inside of the database. But it tells Postgres, oh, hey, somebody's reading the logs. And they haven't read this one yet, so keep it until they come back and they read it. That beautifully works. That worked beautifully. It solved that problem. And with replication slots, combined with streaming replication, building on top of the write-ahead log, we actually have a great physical replication solution where the logs don't disappear, the replica can stay current, and have a very low lag from the master. And with all of this in place, we started thinking, what if we could make that wall sender process smarter? What if we could upgrade the brains of that guy? What if that guy could understand the records that he's reading instead of just blindly sending the bytes over the network? So in Postgres 9.4, still a number of years ago, Postgres introduced something called logical decoding. And what logical decoding did is it did exactly this. It just made the brains of the wall sender like a whole lot smarter. That the wall sender now, he can understand the changes that are happening. He can group them by transaction, and then he can keep track of the status of those transactions. If a transaction aborts or it rolls back, we'll just throw it away. If a transaction commits, then at the point that it commits, then we can ship that thing over the network to wherever the destination is. And then Postgres did something that is like totally the Postgres style of doing things. And they made that little piece that sends it over the network, they made it a plugin based idea, which is like, yeah, the more you work with the Postgres thing, you see this is very much like something they like to do, to have things be extensible and pluggable. So what that means is, maybe I want to build some kind of a service that consumes all the changes coming out of a Postgres database. But I'd like to get it as JSON. OK, so I just use the JSON plugin. And now the wall sender, when it sends those changes over the network to my service that I just built, I get it as JSON. Or maybe I want it as raw SQL. You can do that too. You just use that plugin. And then any downstream system that's able to understand simple basic SQL statements can receive those changes as SQL, and you can plug them in down there. With all of this in place, we're finally in the position to sort of introduce what was actually a real big announcement last year in Postgres 10. And we called it logical replication. But really, if there's one thing I want you to take away from this little part of our talk today, it's this. I want you to see that the big logical replication announcement in Postgres 10, it was not like this big feature that was built from the ground up, merged into Postgres 10, and shipped out. It was actually just this small layer on top. Because in this, again, by the way, going back to what you see this also when Jim talked about partitioning. You see the way the Postgres database is developed, and this is kind of an important thing to understand, is that it's very common for them to iterate on features. Right? So they'll get kind of a core functionality in, and then they'll harden that, they'll mature that, they'll work that out, and then they'll add a little bit more the next year, and then they'll add a bit more the next year. It's a great process. It's not super marketing friendly sometimes, but it results in a wonderfully engineered piece of software. So last year in Postgres 10, we got logical replication, which really, the three really big pieces that I see that were left to do were the SQL, well, first you need a process to apply the changes on the far side, receive it and apply it. Then you need some SQL syntax. You got to work that out. And you got to work out a security model. So what needs super user and what doesn't? How are you going to do grants and privileges and things like that? But this was all built on top of logical decoding. Well, let's take a look at that, actually. Let's go back to our other slide. You see, we have physical replication in Postgres. Read replicas are built on, they leverage the log, for the efficiency of it. They're built on streaming replication and replication slots. We have the database migration service, and there are a whole bunch of third-party solutions for taking data and streaming it, all the changes out of your Postgres database. Those are built on the log for efficiency, streaming replication, replication slots, and the logical decoding framework that we introduced in Postgres 9.4. And then we have the publication and subscription. In Postgres 10, the logical replication that was introduced there. And that's, again, built on the log for efficiency, streaming replication, replication slots, and the logical decoding framework that's been in there since 9.4. So if you're looking for a logical replication solution in Postgres today, it makes all the sense in the world to start by just taking a look at what's baked inside of the engine. It's simple. It's available. It's just a couple of simple SQL statements. You can create publications where you, on a table-by-table basis, if you want to, you can say, this table, publish the changes for this table, and then over in another database, you can say, I want to subscribe to that publication and receive all those changes. Yeah, it's efficient. It's simple. It works well. It is also worth mentioning one other important choice that you have on RDS as well, which is that we have an extension called PG Logical. Quick word about extensions, because this is a concept that not every database has. An extension in Postgres is really almost like another piece of code that can kind of plug into the database to give it skills that it didn't have before, make it sort of like upgrade its capabilities. Sometimes extensions can be even, that separate bit of code could be maintained by a different group of people, maybe an overlapping group of people. A really fairly widely known one is the geospatial capabilities. There's an extension called PostGIS, and it's a whole community of people that maintain this code. You plug it into your Postgres, and then when you type, it's a SQL statement that says create extension, and when you do that, create extension, it will load everything in, and it will really, it's like adding all these capabilities to your database engine that you didn't have before. We also have one called PG Logical, and PG Logical is a logical it's a set of code that will enable Postgres to do logical replication. It's been around for a bit longer. In fact, I wouldn't be surprised to see some more capabilities trickle from PG Logical over the coming years into the core stuff. Some of the people that work on PG Logical are some of the same people that have been helping develop the logical replication capabilities in core Postgres. So if you need support for older versions of Postgres, if you need a little bit more sophistication in how you handle conflicts or DDL or sequences, take a look at the PG Logical extension as well. So logical replication is something I was really excited to talk about. But this last topic, I actually think this might be the single most important thing that we cover during our presentation today, which is monitoring. When you think about monitoring in RDS, I would like you to think about monitoring in terms of 4 main tools that you have in your tool belt: performance insights, enhanced monitoring, CloudWatch, and then third-party solutions or custom things that you build yourself on top of our API. Performance insights is one of the things I was just telling somebody before the talk started. I'm a huge fan of performance insights. I've been talking about it with everybody that I talked to over this past year. Performance insights is like having a window into the inside of your database to see what's really going on. In a nutshell, what it's showing you, at any given point in time, you have a whole bunch of connections. Some of those connections are active. They're processing a SQL statement. Some of them are not doing it. They're idle. And what performance insights is just summarizing the active sessions for you. So like in this picture over time, and it's going to tell you what SQL statements are currently running, but then it tells you more than that. It tells you what they're doing. And even it'll break down each SQL statement to tell you, for that SQL statement, maybe 60% of the time was on the CPU, but maybe 40% of the time I was doing I/O. And then you can go from there, and you can pull maybe your query plan or your execution plan, and you can drill down on it. But the great thing about performance insights is that with performance insights, I'm able to much, much more quickly get straight to where I need to go next. In addition to query plan, one other point or thing I want to point out is that we do, now on Aurora, this is on by default. It's not always on by default in RDS Postgres. There's another extension. There's an extension called PG Stat Statements, and this gives you detailed statistics about the SQL statements that are running in your database. Generally, I recommend for people to turn this on because the value of that data is huge when you're trying to troubleshoot systems. It'll tell you things about the average execution time, how long does that SQL usually take to run, which you won't get from PI won't tell you, did this SQL run for 30 seconds or 23 seconds, but it'll tell you it was running. So you need the statement stats to pull things like that. One other kind of quick tip I wanted to throw in today is that I normally do this, but I've seen this one super clever thing that a couple customers did, and it's actually worth passing along, which is put a comment, if you're able to, sticking a comment at the beginning of your SQL statement with just something unique in that comment. Like a file name and a line number, a GUID, something. But the key is it's searchable. And the really clever thing there is that when a SQL statement pops to the top of Performance Insights or PGStat statements, what that enables you to do is oh, there's that string. I can search on that. And like in basically like a second, you're right at the line of code in your application's source code. You know exactly where that SQL statement was coming from. And trust me, I've spent so much time working with people and trying to figure out, okay, exactly which part of the code was running this SQL statement, because there's like 3 different places that look like maybe they could have made that SQL. Clever little trick that I wanted to sort of mention, just because I've seen that turn out to be so useful. Now, where Performance Insights is like having a window into your database, I think of enhanced monitoring as having a window into your operating system. It's almost like being able to log into the box with a shell. You can see your top processes list. You can see a whole bunch of metrics from things like page tables to memory, detailed memory statistics, the load and the CPU usage, I/O stuff about what the operating system is doing. The one thing that I do want to point out with enhanced monitoring that I often find myself telling people is to pay attention to the granularity. So when you turn it on, you can choose how frequently do I want snapshots? Every 15 seconds do I want to take a snapshot? Every 10 seconds? 5 seconds? Every second? Literally just last week I was working with a customer and we were trying to answer some questions. And even though they were on an old version of Postgres, with enhanced monitoring, we could identify the exact second when the kernel changed its behavior because of memory pressure on the box. And that level of granularity is invaluable when you're troubleshooting. So I mean, I would encourage you to flip on EM and run it with a low level of granularity. That don't do it at like a minute. It's really valuable to have less than that. Finally, CloudWatch. And CloudWatch has been around for a while. But the thing that I find most valuable about CloudWatch is not just the metrics, but what you can do with them, right? So you can use CloudWatch to make sure that you get alerted that you get a page or a notification of some kind if a threshold gets crossed. And there's 4 things that I find myself often telling customers to keep an eye on, and it's worth sort of pointing out right here. First of all is your transaction ID usage. So Postgres we have a metric that will tell you how many transaction IDs have been used. And basically what this is giving you is it's telling you, so in Postgres, there's sort of a garbage collection process that's called vacuum, and it's an important thing to keep an eye on. And what you kind of just want to know is that there's a metric that'll tell you about your transaction ID usage, and if you zoom out a little bit, you should be able to see there's kind of a normal range that thing runs in, and you want to know if it goes outside of that range. So setting an alarm such that you know if this is doing something unexpected. Secondly, there's a metric called, and this is a new one, called DB load, or database load. And this is coming from Performance Insights. And what it's telling you is at any given point in time, it's real simple. It's actually just telling you how many of my connections are doing something right now. The neat thing about that metric is that if you build an alarm on that, and I've actually been doing this for years, even on like other database systems and other places, and I've found that simple little metric, it can catch CPU problems. It can catch all kinds of problems, because often when something happens, one of the ways it manifests itself is SQL might slow down. And if SQL slows down, your number of active connections starts to go up as your application picks up more connections from its connection pools. So this metric can alert you if there's a CPU problem or a whole bunch of other things. The third thing that you need to watch is memory. On any database, really any database, it doesn't matter the engine, when you have high connection counts, memory management is of paramount importance. To quote a colleague of mine, actually, who says that. It's really true. And it's certainly true with Postgres. So we have a couple of CloudWatch metrics, freeable memory, swap usage. You want to keep an eye on this too. It's just one of those things that it's good to be proactive. This is something that's good to watch and possibly alarm on. And the final thing is your disk usage, right? It sounds kind of like old school a little bit. But your disk usage, for most people, it's going to be a line with a slope. But the thing you probably want to know is if that slope changes unexpectedly, right? A little bit earlier, I talked about replication slots. You could, as one example, you could build a service, and your service is using the logical decoding framework so you can efficiently consume all the changes from the database. Well, what if somebody shuts down that service for one reason or another, and they forget to clean up the metadata in the database? The database doesn't know if that was temporary, if they're going to come back online in 15 minutes and they need those logs, or if they're shut down permanently. So it's actually possible that you could accidentally get into a situation where you've shut something down, the database is not able to clean up logs. They're going to start using disk space. That's the sort of thing that the sooner you find out, the better, right? If you find out 3 or 4 days down the road, you have a lot more work to do with dealing with it. And it's great if you can find out quickly with these sorts of things. So it is slightly crazy to try to cover 5 different topics in a deep dive session that's only 1 hour long. But we've given it our best shot, and I think there's a lot of valuable stuff in there. I'm just going to leave this slide up, and Jim and I will be available for questions over here on the side if anybody wants to come up and chat. Thank you.